In the previous video, we have already discussed different types of a closed-loop system based on the controller that it uses. There is a closed-loop system with an on-off controller, proportional controller, integral controller, PI, PD, and PID. There are still many types of controllers, but those that I have just mentioned are the controllers that we are going to discuss in this course. In the previous video, I also mentioned that we can classify closed-loop systems based on the system type. I didn't really discuss in the previous video what system type is, but we will discuss it in this video. We will discuss what system type is. Let's start by considering a unity feedback system as you can see in this slide. This unity feedback system has open loop transfer function of GS. Since this is a unity feedback system, therefore the open loop transfer function will be equal to the forward loop transfer function. Therefore, the closed loop transfer function that represent the relationship between C and R can be written as you can see in the bottom side of this slide. C over R, the transfer function, is equal to G over 1 plus G, where again G is the open loop transfer function of this unity feedback system. Now let's take a closer look on this unity feedback system. Let's now consider a unity feedback system where the open loop transfer function looks like this. If we look at the open loop transfer function in here, the open loop transfer function of the unity feedback system has n number of poles which are equal to 0. So again, this open loop transfer function, the open loop transfer function of this unity feedback system has n number of poles which are equal to 0. For this kind of system, this kind of unity feedback system, we call this unity feedback system as a type N system. So type N refers to a unity feedback system that the open loop transfer function has n poles that are equal to 0. Type number is pretty important because when type number increases by any means, if we have a chance to increase the type number of a unity feedback system, that system accuracy will also increase. But there is a risk when we don't carefully design the controller. The unity feedback system might result in instability. Before we continue discussing the system type, I want to bring you back to the discussion of error. So let's consider again a unity feedback system that you can see in this slide. The error E here represents the difference between R, the reference input, and C, the output of the system. I like the example of air conditioning system. So owing to that example, C corresponds to the temperature in our room, R corresponds to the setting temperature that we set in our air conditioning system remote controller, right? Which means if we have a good air conditioning system, after a few minutes, after we turn on our air conditioning system, if we have a good air conditioning system, C, the temperature in our room, should be equal to R. That should happen when the steady state condition has been reached. Again, of course, that will happen if we have a good air conditioning system. If that condition applies, if we have a good air conditioning system, and when the steady state condition has been reached, C should be equal to R. The temperature in our room should be equal to the temperature that we set in the remote controller. And if that condition happens, C equal to R, that means E in steady state condition should be equal to 0. How do we calculate the steady state value of the E? The steady state of the error can be evaluated using the final value theorem, where the steady state value of the error will be equal to limit s to 0 of s times Es. Where do we get Es? Es can be calculated using this formula. Of course, you know how to derive this formula. E over R can be calculated because we know E is equal to R minus C. So E over R will be equal to R minus C over R. And then if we apply, if we manipulate this equation mathematically, we can get this form of E over R. E over R, then it will be equal to 1 over 1 plus G, where again, G is the open loop transfer function of our unity feedback system. So from here, once we know E and we know the input R, we should be able to calculate the steady state error. Limit s to 0 s times E, where E is equal to R times 1 over 1 plus G. If we know R, we should be able to calculate the steady state error. And again, once more, this steady state error will tell us how good our system is, how good our air conditioning system is. If we have a good air conditioning system, the steady state error should be equal to 0, which means when the steady state condition is reached, C should be equal to R. Now, let's go back to system type things. Let's consider again if to our unity feedback system we apply a unit step input. From the previous formula that calculates steady state error, the steady state error for unit step response can be calculated from this formula, right? Limit s to 0, s times 1 over 1 plus G times the input R, where in this case, because we have a unity step input, the unity step input in Laplace domain is equal to 1 over S. This S, of course, will cancel this S, and then at the end, the steady state error due to unit step input will be equal to 1 over 1 plus g, where s is equal to 0. So this basically tells us the steady state error when a unit step input is given. The ESS for unit step input. That's how I indicate it. If, let's say, now I define a new variable KP, which I refer to as a static position error constant, and I define KP equal to limit s to 0 of GS, or technically then it will be equal to G0, G when all of the S's are set to 0, then I can formulate the steady state error of unit step input as you can see in this equation. The ESS unit step, then it will be equal to 1 over 1 plus Kp, because Kp basically is equal to this value, right? Be careful in here. Kp in this slide refers to static position error constant. It's not the same as Kp that we discussed in the previous video when we were discussing proportional controller. So this Kp is different than the Kp of the proportional gain in our proportional controller. Now, what Kp will tell us? Let's say if we have a type 0 system. What does it mean? Type 0 system means we have a unity feedback system where the open loop transfer function doesn't have poles that is equal to 0, because the n in our system type is equal to 0 here, right? So as you can see here, we have s power of 0 in here. We don't have pole that is equal to 0. If we have type 0 system, a system where the type number n is equal to 0 in this case, then the static position error constant Kp, using the previous formula, limit s to 0 of Gs, if you substitute 0 to all of the s's here, will be just simply equal to the gain of the open loop transfer function. This means then if you have type 0 system, the static position error constant will be a finite number. What happens if we have type 1 or higher system? If we have type 1 or higher, we will have pole or poles in the open loop transfer function of the unity feedback system that is or that are equal to 0. For type 1 system, the n will be equal to 1. For type 2 system, the n here will be equal to 2, and so on and so forth. That means we definitely have pole or poles that is equal to 0. In that case, if you calculate the static position error constant, you will get infinite value for the static position error constant. Okay, so you will only have static position error constant equal to a finite number when your system type is equal to 0. Other than that, the static position error constant will be equal to infinite. So to summarize what we just discussed, for a type 0 system, static position error constant Kp is finite, because the steady state error for a unit step input is equal to 1 over 1 plus Kp. That means the steady state error for a unit step input will also be finite number. For type 1 or higher system, the static position error constant Kp is infinite. If we apply the formula to calculate the steady state error for a given unit step input, which is equal to 1 over 1 plus Kp, this is the steady state error of a system of a unity feedback system with a unit step input, you can easily find that the steady state error for a unit step input will be equal to 0. Okay, that means for type 0 system, if we give a unit step input, we will always have a steady state error at the end when the steady state condition is reached. While for type 1 or higher system, the steady state error, if a unit step input is given to the system, will always be 0. This means, obviously, the accuracy of type 1 or higher system will be better than the accuracy of type 0 system, because for type 1 or higher system, the steady state error is always 0. To conclude, from the given analysis, step response of feedback control systems, in particular for unity feedback systems, will have a steady state error if there is no integration in forward path. What I meant by no integration is a system that has no S part in the denominator, right? So that means when I say there is no integration in forward part, I'm referring to a type 0 system, because for type 0 system, we don't have pole that is equal to 0. If 0 steady state error is desired, that means obviously we have already discussed it, the type of the system must be at least equal to 1. Because when the type of the system is equal to 0, we will always have a finite steady state error when a unit step input is given.